In this video, we will use the formula for the length of a curve to investigate several more examples. So let me remind you, if you have the curve y equals f of x from x equals a to x equals b, the length of that curve is given by the integral here. Now, as I mentioned in our previous video, that from the form of this integrand, the square root of this quantity, this could be a very difficult integral to evaluate. So we have to be very careful in terms of which function we give you so that this is something that can work out algebraically for us. So we're going to investigate two examples that involve some similar algebra, and we'll see kind of a technique that will allow us to handle these. So let's find the length of the curve given by x to the fifth over 6 plus 1 over 10x cubed for x values between 1 and 2. So let's just start by writing down our function f, its derivative, and its formula when it's squared. So we have our function f of x is 1/6 x to the fifth plus 1/10 x to the minus 3. So f prime x is going to be 5/6 x to the fourth minus 3/10 x to the minus 4. What we are going to need is f prime of x squared. F prime of x squared, well, if we imagine squaring this, 5/6 x to the fourth minus 3/10 x to the minus 4. What we are going to get is the first term squared, so 25 over 36 x to the 8th, and then we are going to get 2 times the terms multiplied together. So when we multiply these terms together, we're going to have the minus 2, 5/6 times 3/10 x to the fourth, x to the minus 4th. Then our last term is going to be the final term squared. So 9 over 100 x to the minus 8. Now, let's concentrate in on this middle term. X to the fourth times x to the minus 4th is just a 1. 5/6 times 3/10 is going to end up being 1/4 times 2 is 1/2. So this just ends up being 1/2. So we have 25 over 36 x to the 8th minus 1/2 plus 9 over 100 x to the 8th. And what we are going to have in our integrand when we set up our integral is going to be the square root of 1 plus f prime of x squared. So let me go further on here and just note with some algebra here. 1 plus f prime x squared. So if we take our formula from above and add 1 to it, that middle term of minus 1/2 becomes positive 1/2. So 25 over 36 x to the 8th plus 1/2 plus 9 over 100 x to the minus 8th. And here's where I need to make a very important observation. So we took and squared 5/6 x to the fourth minus 3/10 x to the minus 4th. And we ended up with this term here. And when we added 1 to it, the minus 1/2 in the middle became a plus 1/2. So the only difference between these two would be replacing the minus here with a plus, which would replace the minus up here with a plus. So what we actually have is exactly what we started with, except instead of a minus, it becomes a plus. So that's a very important observation. So we end up actually having 5/6 x to the fourth, now because it's a plus 1/2 in the middle, plus 3 over 10 x to the minus 4th. So that's the most difficult part of the problem, is this algebra. Because let's note what happens now when we plug it into our formula. So the length of this curve is going to be the definite integral over how the x values vary, 1 to 2, and we have the square root of the quantity 1 plus f prime of x squared. So this is what goes underneath the square root. And we've simplified this very nicely. So 5, 6 x to the 4th plus 3 over 10 x to the minus 4, and it's all, squared. And the very nice thing here is that the best thing that we could possibly hope to take the square root of would be a square. So the square root sign cancels the square, and we have the definite integral from 1 to 2 of 5, 6 x to the 4th plus 3 over 10 x to the minus 4. So this works out actually extremely well. So now we go through and we anti-differentiate term by term. So we have 5, 6 times 1/5, so 1, 6 x to the 5th. Then we'll have 3/10 times, if we think about x to the minus 4. Minus 4 plus 1 is minus 3. So we have to divide by minus 3, so this becomes minus 1 over 10 x to the minus 3. Evaluate it from 1 to 2. So that means we plug in a 2, we put a minus sign, we plug in a 1. And I'm going to put a dot, dot, dot here. When you write out those terms and say plug them into your calculator to simplify, what you end up getting is 1,261 over 240. And I used my calculator to simplify this for me. So as mentioned, we have to be very careful in terms of the function that we give you. And this is a nice illustration of how we can kind of work through the algebra and make this arc length, or this length of a curve formula, make it work out. The square root of a square simplifies nicely. Let's look at one more similar example. So let's find the length of the curve given here. Note the difference, and it's not a big difference at all. This is a function of y. So that would be, say, g of y, with the y values between 1 and 2. So we need to approach this exactly as we did before. In our formula for the length of this curve, the length of the curve is going to be the definite integral from 1 to 2 of the square root of 1 plus g prime squared dy. So I'm going to go ahead and do a bunch of these calculations to the side to determine exactly what g prime is, g prime squared, and finally 1 plus g prime. So g of y is y to the 4th over 4 plus 1/8 times y to the minus 2. So when we differentiate this just term by term using our power rule, we're going to have y cubed minus 1/4 y to the minus 3. And we need to think about what this will be when we square it. So g prime of y squared is going to be the first term squared, which is y to the 6. Then we're going to subtract away 2 times the terms multiplied together. So 1/4 y cubed y to the minus 3 plus the last term squared. 1 over 16 y to the minus 6. And notice, as we saw in the previous example, in the middle, y cubed times y to the minus 3 is a 1. 2 times a quarter is 1/2. So this middle term is simply minus 1/2. So now when we take 1 plus g prime of y squared, we are going to end up with, instead of having a minus 1/2 in the middle, we have minus 1/2 plus 1. So very similar here. Y to the 6 plus 1/2 plus 1/16 y to the minus 6. And just note the same observation we made before. What we've calculated here is g prime y squared, and that gives us y to the 6 minus 1/2 plus 1/16 y to the minus 16th. So if instead of having a minus 1/2, we have a plus 1/2, that means that we really have the similar quantity squared, but a plus. So this is really equal to y cubed plus 1/4 y to the minus 3 squared. So very similar to that last example. So let me go ahead and plug that in. So it's a definite integral from 1 to 2 of the square root of the quantity y cubed plus 1/4 y to the minus 3 squared dy. And once again, this is a very nice thing. The square root and the square cancel, and then we can simply anti-differentiate term by term. So 1/4 y to the 4th. So in the second term, we have minus 3. So minus 3 plus 1 is minus 2. So we get plus 1/4 over minus 2, so that'd be minus 1/8. Y to the minus 2, and we evaluate from 1 to 2. So this ends up being, we plug in the 2, so 2 to the 4th is 16, minus 1 over 8, and y to the minus 2 is 1/4, and then we subtract away what we get when we plug in 1. 1/4 minus 1/8. And this number, when you plug it into a calculator and simplify, please don't do this by hand, you end up with 975 over 256. And I would just like to finish by maybe making an algebra observation, because I think these steps over here are really the most difficult. So I'm going to just create a teeny bit of space here. And I'm going to note that what we're really doing is we're comparing a plus b quantity squared with a minus b quantity squared. So we started off with a minus b quantity squared. A squared minus 2ab plus b squared. And note the relationship. If it's a plus b quantity squared, it's a squared plus 2ab plus b squared. So it looks exactly the same, it's just that sign in the middle term. So notice here the sign in the middle term went from minus 1/2 to 1/2, which is why we went from a minus b squared to a plus b squared. Hopefully that helps a little bit with the algebra.